As I've mentioned in previous videos, I don't intend to spend too much time discussing the exhaust or expansion part of the engine. There are a couple of reasons for this which I've already outlined. Firstly, although there are some non-trivial or difficult issues with the design of the exhaust, these are fairly minor compared with even those which beset the intake, and very minor compared with the air-fuel mixing system, which I intend to discuss in much more depth. Secondly, the principles which govern the expansion system in scramjets are not dissimilar to those which control rocketry or jet engine systems, and therefore are extremely well tried and tested in the field. There is also a great deal of experimental work and theoretical study in the area, much more so than in other scramjet topics. So instead of discussing a topic in great detail, I'm just going to look at some of the basic principles to help you to understand some of the other internet resources which are available. I've already mentioned the IIT videos, but there are many other videos and websites available which describe supersonic expansion through nozzles and exhausts and can help you to understand this. And there's also excellent coverage of this in the books which I referred to in video 8. Key to understanding nozzles is understanding converging and diverging ducts. It's easy to show mathematically that these have the opposite effect at subsonic and supersonic speeds. For example, in a converging duct below Mach 1 at subsonic speeds, the flow speeds up as it travels through the duct. However, at Mach numbers greater than 1 at supersonic speeds, the flow slows down through a converging duct. By contrast, a diverging duct has exactly the opposite effects. At Mach numbers less than 1 subsonic speeds, it slows the flow down, and at supersonic speeds, it speeds the flow up. These two facts explain the configuration of a rocket engine. The flow leaving the combustion chamber is subsonic, and the initial converging duct therefore speeds it up. It hits Mach 1 when it reaches the throat. The flow is then supersonic, so the diverging duct section speeds this up further to give a high exit velocity. Remember that the thrust of the engine, F, is equal to m dot v, where v is the exit velocity. The trick is to design a duct so that it will operate well given the pressures at either end, that is, in the combustion chamber and at the ambient pressure at the exit of the nozzle. When the nozzle is working correctly, the throat is at Mach 1 and is said to be choked. M dot is at its maximum value. Understanding this system, although it doesn't seem to have much to do with scramjets, gives you a good picture of the operation of these ducts and nozzles both at subsonic and supersonic speed. Having said all this, and that the scramjet design is not so much of a problem as the other scramjet systems, there are several points to note. The nozzles in scram systems are often planar as opposed to axisymmetric. We discussed this in a previous video about intakes. This is to achieve good airframe engine integration, which is considered essential to minimize drag. Most of the discussion and analysis you will see of ducts in literature concerns axisymmetrical designs. Secondly, flow from a combustor into the nozzle is already supersonic, so the duct itself is generally divergent, rather than the convergent divergent type we have in rockets. Generally speaking, this actually makes the analysis simpler, because we only have to consider supersonic flow speeding up through a diverging duct. Finally, the planar design of a duct often leads itself to newer experimental types, such as the aerospike, also called the cone or free expansion type duct. This is a new design which lends itself to experimentation.